So here we're going to look at the stretch reflex, just a simple overview of the entire reflex. So when you look at your muscle fiber, the content that you see outside, that is called your extrafusor fibers. This is that in red. But when you cut that extrafusor fiber open, inside you're going to find intrafusor fibers. So there are two sets of them. So the ones that are just linear in that manner, these are called nuclear chain fibers because their nucleuses are in a linear manner. The nucleuses are in a linear manner like that. But there are also the others that are bulged at a certain region. So these are called nuclear bag fibers. And then the nucleuses are in clusters like that. So these fibers that you're seeing here, they only have contractile filaments in their peripheries here, and in the peripheries there, in the peripheries here, in the peripheries there. So at the center here, they do not have contractile fibers. They do not have contractile fibers. So at the center, they don't contract. They only contract in the periphery. At the center here, the center just serves as a sensory region. It just serves as a sensory region to sense the stretch. All right, so this is your basic anatomy. And then in terms of innervation, you can see here that you have type 1A afferent fibers. So these mainly surround your central part of both the static. So these nuclear chain fibers are also called static fibers. And then these nuclear bag fibers are called your dynamic fibers. So static simply meaning they are going to be sensing static stretch. Yeah. So stretch that is not changing. For example, standing. Yeah. So static, standing. And then these dynamic ones detect stretch that is ever constant. So let's say you start walking. So as you are moving your leg, you are moving the tone of how the muscle is being stretched. So yeah, so you have that. So the type 1A, they do both the dynamic and they also do the static, where you have the other ones. These are the type 2 afferent fibers. So the type 2 afferent fibers are strictly static. These guys are strictly static. Okay, so you're going to have this setup. And then you're going to have motor neurons coming to these same intrafusor fibers. So these are the gamma neurons. These gamma neurons are going to attach to the contractile portion of your intrafusor fiber. So it's going to attach here and it's going to attach here. So it's going to go something like this, something like this. Okay, so these contract the peripheral portions so that the central portion remain extended, because if the central portion, which is the sensory region, becomes too clumped together, it loses its sensitivity. Okay, so let's say you have this type of a setup. So let's say you have a setup where you have, let's say this is your overall muscle. And then inside here, you have your intrafusor fibers there, and the central portion here is the sensory part. Both kuli nuclear bag na kuli ka nuclear chain. So when your muscle starts contracting, what is going to happen is that it's going to be reducing. So this stretch reflex detects stretch. So the initial stimuli is stretch. So when you stretch your muscle, meaning you're going to be going outward like that. Okay, so your muscle is going to go in that direction and that direction. Even your intrafusor fibers are going to go in that direction and in that direction. So that is initially. So the response of the stretch reflex is to initiate contraction of the extrafusor fibers. So when the extrafusor fibers contract, these red ones, these red things out here, it's going to bring your muscle back like that and back like that. Now, when your entire muscle goes inward like that, even your intrafusor fibers is going to be contraction inward like that and inward like that. So what's going to happen is that this central portion is going to be compressed. And when the central portion is compressed, it loses its sensitivity. Yeah, sensitivity is lost. Sensitivity is lost. So to maintain the sensitivity, we don't want the central portion to be squeezed. So what's going to happen is that we're going to have the gamma neurons that are going to come and innervate the peripheral portions, the portions of the intrafusor fibers that have contractile filaments, and initiate them to contract. So when they contract, it's going to be like this. So the overall muscle outside is contracting the muscle like this, but the gamma motor neurons that are going to innervate the contractile portions of the intrafusal fibers, are going to make them, okay, so let's say this is your gamma intrafusal fiber, then this is your central portion. So your gamma motor neurons are going to make sure that those contract like that. So your overall muscle is contracting inward, but your intrafusal fibers, then they are contracting outward with the help of the gamma motor neuron attaching to the peripheral portions that have contractile filaments. That's basically what happens. Okay, so let's look at it from this lovely diagram here. So let's pretend this is your arm. So this is your forearm, and this is your arm. This is your arm. And then let's say I put a box on your hands. So that box is going to make your arm go downward. And when that arm goes downwards, it's going to stretch this muscle here. This muscle here is going to be stretched. So when this muscle is stretched, these afferent fibers, specifically the type 1A fibers, are going to send signals to your spinal cord. And let's keep in mind that it is the ventral horn that deals with motor innervation, and this guy here, the stretch reflex, is a monosynaptic reflex. So this afferent neuron comes here and then it synapses with the effector neuron of the same muscle and releases excitatory neurotransmitters. So once it does that, it's going to synapse with two neurons. The first neuron is going to go to the extrafusal fibers. This is what you call the alpha neuron. Going to the extrafusal fibers, making the entire muscle contract. Okay, so first you had stretch. Stretch being transmitted by the type 1A takes it to the alpha neurons, and the alpha neurons initiate contraction of the same muscle. Contraction of the same muscle. But if we're going to have contraction of the same muscle, then we must have relaxation of the opposite muscle, because if both muscles, the one in front and the one behind, contract, you won't have effective lifting of this limb. So you want the opposite muscle to relax. How are we going to make the opposite muscle to relax? We are going to have an inhibitory interneuron right about here. So from this neuron, you're having excitatory neurotransmitters, but from this relay neuron at the center here, you're having inhibitory neurons. You're having inhibitory neurons. So these inhibitory neurons inhibit the antagonist muscle, causing it to relax. Okay, so the initial muscle that sensed the stretch, the final result is going to be contraction. But the antagonist muscle, the opposite muscle, the final result is going to be relaxation. Why? Because you have an inhibitory interneuron in the center. Yeah, you have an inhibitory interneuron in the center. Now, with the same muscle, we said we have the alpha neurons. You also have the gamma neurons. Do you remember the roles of the gamma neurons? The gamma neurons are supposed to maintain sensitivity. So when your type 1A alpha 1A fiber comes in the spinal cord, it ends there. So it's going to synapse with two neurons. They haven't just shown it here. So one is the alpha neuron going to the extrafusal. The other one is the gamma neuron going to the intrafusal. Specifically, where in the intrafusal? The periphery portions that have contractile filaments. Okay, so this one here makes your overall muscle contract in this fashion. But remember, when we have compression of the central regions, of our intrafusal fibers, we're going to lose sensitivity. So we're going to have this. So this one, the one responsible is the alpha neuron. So we're going to have the gamma neuron here and the gamma neuron there, making the intrafusal fiber contract that way, so that we don't have compression of the central portion. So the entire muscle is contracting like that, but the intrafusal fibers are contracting outwards. And that's how you maintain sensitivity. So alpha motor neuron contract the extrafusal fibers. Alpha or gamma neuron contracting the intrafusor fibers, and that's how you have your stretch reflex. Another concept in the stretch reflex is what you call your alpha gamma co-activation. So this is where you have both the alpha and the gamma being activated at the same time. Now this happens even from our initial setting, this one here, where you have something stretching your muscle, and then this whole thing is activated, because we're seeing that this 1A is activating both the alpha and the gamma. So that can also be called alpha gamma co-activation. But another source of your alpha gamma co-activation are descending fibers coming from your brain. Specifically, they come from 4 regions in the brain. So they'll come from the cortex, they'll come from the cerebellum, because basically your stretch reflex helps you maintain posture. We said when we're standing. So for us to maintain that posture, our muscles are supposed to contract. They're supposed to have a certain tone to them. So how do we maintain that tone? It is through the same stretch reflex. Alpha neurons, gamma neurons, inhibitory interneuron. And then you also have centers like the vestibular nucleus. These are the centers in the brain that are really, really very much involved with balance and posture. So these send descending pathways to your muscles, and they can cause the alpha gamma coactivation. The one that's inhibitory is the reticular formation, the one found in the medulla. So that's your medullary reticular formation. This one contributes inhibitory neurons, while all these others contribute excitatory neurons. Okay, so the reticular formation in the medulla inhibits your alpha gamma coactivation. Okay, so it inhibits your stretch reflex. So this means that any tract that you know that comes from the medulla and comes from the reticular formation inside the medulla, it's going to cause inhibition of the stretch reflex. So among the descending fibers that you know, there should be a descending fiber that comes from the reticular formation. Yeah. Quite about reticulospinal. Ingekho have reticulospinal, specifically medullary reticulospinal. Yeah. So that one is going to inhibit the stretch reflex. So go to your descending fibers PPT, look at specifically the reticulospinal. There are 2 of them, because there's a reticular formation in the medulla, then there's a reticular formation in your pons. So the one in the medulla specifically is going to inhibit the stretch reflex. So once you have it here, you have your descending fiber coming here. Your descending fiber is going to branch off into a collateral there, and then it is going to excite both the alpha and the gamma motor neuron. So this works mainly when you decide to contract your muscles. When you make a conscious decision to say, all right, let me stand. Let me start walking. All right, walking left, right. So a signal is sent from your brain coming down, and then it's going to activate both the alpha and the gamma. So the alpha, contraction of the extrafusor fibers. Gamma, contraction of the intrafusor fibers. Specifically, where in the intrafusor fibers? Periphery portion, to do what? Maintain sensitivity. And that's basically the alpha gamma coactivation. So alpha gamma coactivation can come from the 1A neuron with the stimuli being stretch, or it can come from descending fibers from your cortex with your stimuli being, a conscious decision for you to contract. And that's basically what you have. So that is a stretch reflex all in all. So a functional stretch reflex that we've talked of, passively, but just to clearly point them out. So number 1, to maintain your muscle tone. Number 2, to maintain your posture. So these are the main ones. So to control your muscle tone and to maintain your posture. Okay. So muscle tone. So when you excite your alpha neurons very much, then you're going to cause, increased tone. Yeah. When you excite them little, reduce tone. When you inhibit them, you're going to bring about relaxation, just as what is happening with the opposite muscle. So if this is the OG muscle, the antagonist muscle kunuma is obviously going to have an inhibitory interneuron causing it to relax. But otherwise, yes.